in-back paradigm, presentation time, effects depend on memory load and age. I'm Ellie Varn.
I'm Lindsay, Cooke.
And I'm Lani Smith.
Okay, so the main task that we used for our research was the in-back task. So this task is commonly used to measure working memory capacity. And so it requires you to constantly update and store stimuli while also simultaneously making decisions about the stimuli on the screen and previous stimuli. So to further explain it, this is an example of the one-back task. So each letter would appear one at a time on the screen, and you would have to compare the B to the A, so the stimulus on the screen to one back. And so this is the two-back task, and so you would again compare the C to the A, so two back. And then this is the three back, and again, you would compare the current stimulus to three back. And so to help you guys understand it more, we thought it would be fun to have you all complete a three-back task with us. So you'll be presented with a series of faces, and you'll have to say yes or no out loud. Participate. If the face on the screen is the same as the one that was three back. So we're going to get, and then the first three photos that you see will all be no, because you have nothing to compare them to for three back. So, is this the same?
No.
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 No. No. Yes. No. 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 Yes. No. Yes.
All right, nice job. That was good. Okay. So for our task, we used letters instead of faces. And so for this figure, each black box represents the computer screen. And so the boxes with letters in them represent the stimuli. And then the blank boxes represent when the letter is not on the screen. And so the time that the letter is on the screen is the stimulus time, and the time that the letter is not on the screen is the blank time. And so the stimulus time plus the blank time is equivalent to the total time. And so we can manipulate the stimulus time and the blank time in order to make the task more difficult. And so this is an example of the typical accuracy results for the in-back task. So the x-axis here is task load, so one back, two back, and three back. And the y-axis is D prime, which is just a sensitivity measure for accuracy. And so as you can see, as the task gets more difficult, from 1 to 2 to 3 back, accuracy declines.
And so this is the embedded processes model of working memory, which was done by Oberauer, and he has a model of working memory that's different than any other. And so in the middle we have the focus of attention, and it has a capacity of 1. And then outside of that we have the region of direct access, which has a capacity of about 4 to 5. And then outside of that we have the activated long-term memory. And so what happens is when you're presented with a piece of information, it enters into the focus of attention, and then as another piece is also presented, the previous piece moves into the region of direct access to make room for the new piece to move into the focus of attention. And information can move from the region of direct access back into the focus of attention for means of comparison, and this comparison process can be interrupted by information in the activated long-term memory, which is there from previous knowledge. And so I'm going to show you an animation of how this model works in terms of the in-back task. On the right side of the screen we have letters that are going to stay there the whole time. That's the sequence that the participant would be presented with for the three-back task. And then on this side of the screen we have a box, which is what the computer would show, and the black stimulus is what the participant is presented with at that time. So if the participant is presented with an L, it moves into the focus of attention. And then the participant is presented with an S, and so the L moves into the region of direct access, and the S moves into the FOA, and they are not compared because it's a three-back task, and so that would be one back, and so the decision would be no. And then the participant is presented with a T, and so the S moves into the region of direct access, the T moves into the FOA, and then again the decision would be no because the L would be two back, not three back, and then the participant would be presented with an L, the T would move into the region of direct access, the L into the FOA, and then the other L would move back into the FOA for comparison, and the decision would be yes.
Okay, so throughout the literature we can see that as people age, working memory deficits do occur. And so here on the screen is a foundation article in the field of working memory and aging by Verhagen and Mazat, 2005. And here's a graph from this paper. On your y-axis you have the percent correct, and then on the x-axis you have your impact value. And here they're comparing younger and older adults on an impact task. And as you can see here, at the one-back task, older and younger adults are both performing at the same level of accuracy. However, when you move into the two-back task, you see that there is an interaction that occurs, and older adults seem to drop significantly more in accuracy than younger adults. This can be explained by availability and accessibility. So availability is defined by the percentage correct, while accessibility is defined as the time it takes individuals to retrieve items that are outside their focus of attention. So when older adults are performing this two-back task, they're having to retrieve items that are outside their focus of attention, therefore taking them a little bit longer and decreasing their accuracy. So the purpose of this current study, we had two. The first was to examine timing manipulations on both stimulus time and total time on performance. And then we also wanted to look at age effects on working memory capacity through the impact task. So to do so, we manipulated total time and stimulus time across three conditions. This is our first condition. It's short, long total time. This is 2 seconds per stimulus versus 4 seconds per stimulus. The stimulus includes the blank time, and it's also worthy to note that blank time here is in red, stimulus time is in blue. Our y-axis is in milliseconds, and our x-axis is the two programs that were within the condition. So within this condition, both blank time and stimulus time were exposed equally to the participant. And then for the short total time, this is our 2-second condition. Participants were exposed to the stimulus 2 seconds, but the stimulus time and the blank time differed. And then 4 seconds here, participants were exposed to each stimulus 4 seconds, but the blank time and the stimulus time also differed. This is a timeline of our experiment. After the experiment, we asked participants to fill out a strategy questionnaire where they basically told us what they did to perform the impact task, and we'll be more than happy to answer any questions you have about strategy at the end of the program.
So we had three main hypotheses, and for each of our graphs, you'll see the x-axis is task load, so 1 back, 2 back, and 3 back. And the y-axis is d prime, which again is just a sensitivity measure of accuracy. So we hypothesized that the long total time group would have better performance accuracy across the task in comparison to the short total time group. And this was hypothesized because the participants would have more time to process and make decisions in comparison to the short total time group. And our second hypothesis was that the long stimulus group would have better performance accuracy across the task, specifically at the 3 back. And we thought this because participants would have more time, because the 3 back task is more difficult, they would have more time to process those stimuli and make decisions in comparison to the short stimulus group that don't have as much time with each stimulus. And our last hypothesis was that the younger adult group would have better accuracy across all conditions in comparison to the older adult group, and that there would be a significant interaction from 1 back to 2 back. And this is because the 1 back is typically a lot easier, but then moving to the 2 back, that becomes more difficult, and so younger adults would be better at that task.
And so for our first graph as results, we compared the short and the long time group combined, which was one was 2 seconds and one was 4 seconds, and we found that there was a significant main effective condition, and t-test showed that it was significant at the 2 back level, which we expected, but we also expected it to be found at the 1 and the 3 back level. But in this condition, total time and stimulus time were confounded since they were both different, and so in a long total time group, we did not find a significant main effective condition, which suggests that stimulus time did not help performance. And then in a short total time group, we did find a significant main effective condition, but the t-test showed that the effect was at the 1 back level, and we expected it to be at the 3 back level. And so again, here's the long total time group for the younger adults. I will show you older adults next, but again, we did not find a significant main effective condition, meaning that the stimulus time did not help performance. But in older adults, we did find a significant main effective condition, so for older adults, the stimulus time did help performance. But we did not find a significant main effective age, and so we think that this is because we had a group of high-functioning older adults who were recruited from a lifelong learning program.
And so we concluded for total time for the younger adults that the longer the total time, the better the accuracy And we think this because the participants had more total time, so they were able to process and make decisions. And connecting back to the model that we showed you earlier, they were able to retrieve the stimuli from their region of direct access and bring it back into their focus of attention. And they had more time to do that in comparison to the shorter total time group.
And for stimulus time, we had mixed findings. So we found that the short total time and the long stimulus time increased performance. And we think that this is because when they had 2 seconds to process the information and the stimulus on the screen disappeared quickly, that they didn't have as much time to shift the information into the focus of attention. But when the stimulus was on the screen for a longer period of time, that they were able to have enough time to shift the information. And then we also found that stimulus time does not have an effect when there's a long total time. And we think that this is because when they had 4 seconds to process the information, that they had plenty of time to shift the information as a whole.
So some implications from these conclusions, it does seem that stimulus time changes performance. Therefore, it's very important when researchers implement the impact task that they should be aware that methodology is important. And for the older adults, the longer stimulus time resulted in better accuracy, and this can be referred back to our Browers model. They had more time to go outside of their focus of attention, retrieve items from the region of direct access, and then make that decision. This is pretty impressive for older adults because it means these items are still available to them. For total time, this is not really known because older adults only completed 1 condition, which leads us to a future direction, maybe having the older adults complete the other 2 conditions. So we just wanted to give a huge thank you to Dr. Bopp. We couldn't have done this without you, Wofford Psychology Department participants, and then Lifelong Learning at Wofford.
We have time for a couple of questions.
I'd love to hear just a little bit about strategies.
So we found that the younger adults, if they had a consistent strategy, it did not help their accuracy. But for older adults, if they had a consistent strategy, it did help. And we recoded all of our strategies, and this is a breakdown of the different types of strategies that people reported that they used that were consistent, but it's only for older adults is when it helped.
Your theory about the high-performing older adults, did you take any other cognitive tests to see if their speed of processing was faster? Or
We
do you
did
have any
an
other spin-off?
O-span test, or task in between our impacts, but we didn't really look at that much because we were using data from last year, and they did a different O-span task. So no, all the older adults really did was, they came in, they completed forms, we learned a little bit about, how long they had education, all that good stuff, but nothing else that really told us about their higher level of processing. So.
Anybody else? Great, thank you.